We are going to start a chapter on chemical equilibrium today. This will be one of your favorite chapters with several labs that we're going to be looking at. Chemical equilibrium, along with acid and bases, as well as solubility equilibria, all fit into Big Idea 6. Students will be able to explain that any bond or IMF that can be formed also can be broken. You'll see these processes are in dynamic competition, and we'll look at dynamic equilibrium in just a minute. Sensitive both to initial conditions as well as external perturbations. Initial conditions will be new to all of you this year. External perturbations is referring to Le Chatelier's principle, which some of you are aware of. It's a very interesting principle. We'll explain it in great detail, and you should be very successful in working problems involving Le Chatelier's principle. So we're going to take a look at chemical equilibrium. We mentioned a smidge about it in the previous chapter. What we're going to be looking at here is we want to know how equilibrium constants are determined from data. We'll be doing that today as well as in the lab. We want to look at how equilibrium constants are calculated from concentrations of substances. We're going to look at how disturbances or alterations in pressure, volume, and temperature affect equilibrium. And then we'll also take a look at what effect, if any, a catalyst has on equilibrium. In terms of equilibrium, we have said previously that at equilibrium, the rate of the forward and reverse reactions are equal. Their rates are equal, and you'll see the concentration of reactants and products being constant when equilibrium is attained. Equilibrium is highly dynamic, not static. For example, you have water molecules in the liquid phase. I'm going to run this, and you'll see that water molecules now will break off from that liquid phase, breaking the intermolecular forces and going off into the gaseous phase. Initially, vaporization rate will be greater than condensation rate, but at equilibrium, the rates of vaporization and condensation are the same. That is chemical equilibrium. It's dynamic because it continues. It doesn't just stop. If we take a look at concentration versus time graphically for a reversible reaction, and let me introduce you to a reversible reaction. Some of you may have seen it previously. In the reaction that is given, we're looking at decomposition of hydrogen iodide gas to hydrogen gas and iodine vapor. The double arrow indicates a reversible reaction. Instead of writing two reactions, that is decomp and synthesis, we instead show the reaction as a reversible reaction. You'll either see it with arrows like that, you could see it with arrows like that, you could see it like that. Any of those indicate reversible, and we'll be looking at this in regard to molecular representation in a bit. Graphically, what you are seeing, and keep the balanced equation in mind, is as you go from left to right from the balanced equation, you'll see the concentration of hydrogen iodide initially decreases over time, whereas the concentration of hydrogen and iodine increase over time. Why would the concentration of hydrogen iodide decrease over time? It is a reactant that is being consumed. Product concentration increases over time because they get generated or produced. Why would the concentration of hydrogen iodide be twice that of hydrogen or iodine? Because the coefficient of 2 signifies 2 times the amount, 2 moles per 1 mole. Why would these be the same?
Because they have the same coefficient.
Same coefficient of 1. What you're seeing there is that at some time TC, those concentrations those concentrations are just plateauing. So they're constant. I gotta get a sucker. Taking a look at ammonia generation. Taking a look at ammonia generation, you can see that 2 moles of ammonia are made from nitrogen gas and hydrogen gas. And again, why are the concentrations of nitrogen gas and hydrogen gas decreasing? Reactants, they get consumed. Why is the concentration of hydrogen gas 3 times that of nitrogen gas? 3 to 1 mole ratio. All right? I've seen questions on the AP exam where you have to draw it in. I've seen questions where you have to explain why the concentration at equilibrium, for example, hydrogen gas is greater than nitrogen gas. With every big idea, there are objectives and also essential knowledge pieces. I don't break it all down for you because it really just is so overwhelming. But in essential knowledge 6A1, it says in many classes of reactions, it's important to consider both the forward and reverse reaction. And it turns out that many readily observable processes are in fact reversible. We looked at evaporation and condensing of water. There are other examples as well. I think probably one of the most interesting examples includes the binding of oxygen to hemoglobin. For example, and this is more biochemical based, but they do like these practical examples, so we do want to take a look at them. Hemoglobin is a protein found in blood. And hemoglobin has 4 oxygen binding sites. And it has what's known as cooperative binding, that is way above the level of this course. But 1 oxygen jumps on, essentially welcoming 3 more. And so there are 4 oxygen binding sites on hemoglobin. Now, oxygen jumps on and jumps off within seconds. It's very rapid. That's how oxygen, which is picked up in the lungs, is delivered to tissues and organs throughout the body. Oxygen has a molecular mass of about 32 grams per mole. Carbon monoxide has a molecular mass of about 28 grams per mole. If we consider the structure of oxygen, we know it has a double bond. We know it's a linear molecule. If we consider the structure of carbon monoxide, we know it has a triple bond, and this is one of the few times that carbon has a lone pair of electrons on it. So it too is linear. It turns out that the same oxygen binding sites can also bind carbon monoxide. But the kinetics here is grossly different. It doesn't hop on and hop off within seconds. It hangs out for hours. can be 8 hours. And this is why carbon monoxide is so deadly. It's a clear, odorless gas, so you can't smell it when it's there. You can't see it. It binds to hemoglobin, preventing oxygen from binding, and you literally just suffocate. With that said, most of you are now driving. I know you think you have the ability to multitask, but when you pull into your garage, get off the phone, stop texting, turn the radio off, and make sure you turn your car off. That is the most important thing, because carbon monoxide, if you close that garage door, will get into your house, and nobody is walking out the next day or several hours later. Be very, very careful. You're old enough to drive. Show you're responsible. Don't close the garage with the car running. Don't start the car with the garage door down. Very, very dangerous.
You answered my question. I was going to ask if you suffocated.
Yeah, you literally just suffocate because the carbon monoxide binds up your hemoglobin, and then there's not enough hemoglobin for the oxygen. And that's, for example, with sickle cell, you have those sickled red blood cells. It's not the same hemoglobin molecule. It's a hemoglobin S instead of an A. It has a single amino acid substitution. And that's enough for those red blood cells to stick together, and they don't have the same oxygen binding capacity. Mommy lecture over, but be careful, and you should have carbon monoxide detectors in your homes. Really important. Check the batteries periodically, because when they go, it's always 2 o'clock in the morning. All right. There are other examples, but that to me is the one that I think is the most important. There are receptor sites in the nose and things like that, transfer of carbon between atmosphere and biosphere, etc. You can look through. We'll get into protons and acid-base reactions a little later on. That one will be very interesting. We've talked about electron transfer and redox reactions. There you can get reversible reactions as well. The equilibrium constant, abbreviated KEQ, K for constant, EQ for equilibrium. And this is going to show a ratio of equilibrium concentrations. You're going to see in the next 3 chapters we talk about there is a whole family of KEQ, equilibrium constant. In this chapter, we're going to talk about KC, and this is going to be for concentration equilibrium constant, KP for pressure equilibrium constant, a little bit different. In the acid-base chapter, we'll hit Ka, Kb, and Kw, and you can get pKa's and pKb's and pKw's. And then in the solubility equilibria chapter, we'll hit KSP. But the key is that this is going to be equilibrium constant, when equilibrium is attained, when the rate of the forward and reverse reactions are equal. When you're writing equilibrium constant expressions, we mentioned this in the previous chapter, you're going to get some practice here. You must do some additional KEQ type solving problems to really understand this concept well. When you're writing KCs, here's your balanced generic equation. You're going to put product concentration on top. So those brackets indicate concentration, concentration of G raised to its stoichiometric coefficient right here. Concentration of H raised to its stoichiometric coefficient right there. Reactant concentration in the denominator, so A concentration raised to its stoichiometric coefficient. Huh?
Like highlight something and leave your mouse where it is. See?
Ah, cool. Learn something new every day. Thank you.
Only the G red and the rest are green.
I don't think I wanted to make that
Christmas.
green though. We should make that like blue.
She wants Christmas to come back. She's Jewish. Well, Hanukkah, whatever.
Yeah, those aren't Hanukkah
Well,
colors.
blue. Now she's in blue.
Yeah, but it's the Hanukkah.
We'll just leave that black.
Blue, green, and
Anyway,
Make it yellow. Now it is.
yellow won't show up. For this one, it says write the equilibrium constant expression or concentration equilibrium constant for the following. Again, product concentration in the numerator, reactant concentrations in the denominator, each raised to their coefficients. You will note that when you have more than one substance on a side, whether it be reactant or product, you are multiplying those concentrations, not adding them. Every year somebody adds them. Don't do that. You can be given concentrations and solve for KCs. You can be given KC and all concentrations except one and solve for the missing one. Shown here as an example. I'm going to work through the derivation on paper. I want to show you a quick trick, and then we'll give it a shot.
Differentiation.
I hate you. Oh my gosh.
Reversible reaction, decomp of hydrogen iodide at 698 Kelvin. You must specify the temperature. If you change the temperature, the value of Kc changes. Produces an equilibrium concentrations in which hydrogen and iodine are both 0.0250 molar and the Kc is 1.84 times 10 to the negative 2. We want to know the concentration of hydrogen iodide. Anytime you do these types of problems where you're solving for Kc or a concentration, you must write the Kc expression. Again, products on top, reactants on the bottom. So Kc is equal to product concentrations, and it's the product of the product concentrations over the reactant concentration. And why am I going to square that?
I'm still kind of confused. What's the difference between KC and KEQ?
Nothing. Kc is for concentration. What you did last year with KEQ was a Kc. You'll see what Kp is. With Kp, instead of putting concentrations in, you put pressures in at equilibrium.
Oh, so it
So
just
just saying
depends
what
on
you
what
use?
What they're giving you. But the Kp is written slightly differently, and we'll get there on Wednesday. They're telling you that the concentrations of hydrogen gas and iodine vapor are both 0.0250 molar. They're telling you that the Kc is 1.84 times 10 to the negative 2, and they want to know the concentration of hydrogen iodide. Now, most of you, all of you in here are math savvy, and most of you will recognize that you can interchange a numerator on one side of an equation with a denominator on the other side of the equation. If you don't see it, you can go ahead and cross multiply, and so it's just time consuming. I think most of you are comfortable with it. But instead of doing all that, you can interchange these two. And then 2 times what fraction equals 1? 1/2. So if I take this to the 1/2, I get hydrogen iodide concentration to the first. And then I'm going to take this to the 1/2 power, or the square root. If this had been a 3, what would that be? 1/3, and a 4, and that would be a 1/4. So at this point, you can just plug and chug away. You've got hydrogen iodide concentration. You have 0.0250 molar, and you have that twice, so we're going to square. You will note that there's no unit for Kc. Kc, Kp, Ka, Kb, unitless quantity. No unit, because each equation could have a different unit, so we just don't use a unit for Kc.
So
Do you
basically
need
they
a
got
unit for any of the KEQ?
Nope. And this is equal to 0.184 molar, unit of concentration, capital M for molar. Problem at the top of the screen. You're looking at the synthesis of phosgene from carbon monoxide and chlorine gas. The Kc is provided, temperature is provided. It says if the equilibrium concentrations of chlorine and phosgene are the same at this temperature, what is concentration of carbon monoxide? How are we going to approach that one? I'm going to rewrite the reaction here just so it's all together. How do we approach this?
You first set up like the case.
Absolutely. Write your Kc, which would be what? What goes in the numerator? What goes in the denominator? So I should add these concentrations? All right. Not going to add them. We're going to multiply. Good. Now it said two of them are the same. So you can just cancel those, right? They're the same. 3 divided by 3 is 1. So if these two concentrations, say 2 molar for both, are the same, bye-bye. So Kc is equal to 1 over carbon monoxide. We want to know the concentration of carbon monoxide, so that's 1 over Kc, right? Yes, yes? Now, let me show you how to do this without a calculator. We have carbon monoxide concentration is equal to 1 over 1.2 times 10 to the 3rd power. One 1.2 is the same thing as 6/5, correct? Now I'm going to flip it, and I have 5/6 times 10 to the negative 3rd. Are you with me?
Yeah.
5/6 is a smidge more than 0.8. I'm just going to do 0.8 for a minute because I think it'll be easy. So I have 0.8 times 10 to the negative 3, and that is 0.8 is 8 times 10 to the negative 1, right?
Yeah.
I'm just going to flip the page. Well, I don't know if you're quite there. I'll write it up here. So that's 8.0 times 10 to the negative 1 times 10 to the negative 3, and that is approximately 8 times 10 to the negative 4. If you did it with a calculator, you would have come out with 8.3 times 10 to the negative 4. But if you're without a calculator, there's not going to be anything very close to that. You just have to be able to approximate. And don't forget the unit M for concentration.
See, that would throw me off, because if I got 8.0, I would just assume my answer wasn't there and try to reduce something.
But if you're estimating...
No, you're misunderstanding. They're going to give you like maybe 8.0 times 10 to the negative 2, negative 3, negative 4, negative 5. So you'll be able to hone in on your answer. Couple more things I want to show you. Can't emphasize enough the importance of being able to write KEQ expressions, solving them, and you need practice. The other thing I want to show you is how to modify an equilibrium constant expression. This is going to look a lot like Hess's law, but it's processed differently. Be careful. It says when a chemical reaction is reversed, the reverse reaction has the inverse KEQ. So you take the reciprocal. For example, if you're looking at the generation of 2 moles of nitrogen dioxide from nitrogen monoxide and oxygen, Kc is here. You can think of it just as a variable. Let's say Kc is equal to A. Comparing this reaction to this, what did I do? I flipped it. So when I flip the reaction, I take the reciprocal of the Kc. I'm calling it K prime. So 1 over A. When you flip the order, you take the inverse, the reciprocal of the Kc. You'll see that in calculus when you take derivatives, right? Prime and I understand that, but it's the same type of thing. You're deriving it from what you started, not necessarily a derivative.
Remember when we did like sets and it was like everything except for that was that prime? It's like not.
Oh.
All right. When the coefficients of an equation are multiplied by some common factor n, that n becomes the exponent for the original Kc you had. So for example, what you're looking at here is here you generated 2 moles of nitrogen dioxide. Here you're generating 1. To go from this equation to this, we multiplied by what? 1/2. So 1/2 becomes my exponent. So if I have A, it's A to the 1/2. Let's take a look here. It says the equilibrium constant for the reaction in which 1 mole of sulfur trioxide is generated is 20. Calculate Kc at the same temperature when 2 moles of sulfur dioxide is decomposed. So looking at this reaction, we saw that in the initial reaction, and this is in your notes, I'm just scribbling down, we had this, and the Kc was 20, and I want to know what happens when you decompose 2 moles of it. So to go from here to here, what did I do? I multiplied by 2 and I flipped. So whatever my Kc was, I'm going to do 1 over that quantity, and then I multiplied by 2. So should I multiply this by 2? No, you square it. And now one of the kids was like, how do you do that without a calculator? I would do this without a calculator the following way. I know 1/2 is 0.5, right? So 1 over 20 is 0.05, correct? All right, we'll worry about the siggy-wiggies after. Well, that is 5 here. I'll put them back. Times 10 to the negative 2, correct? And now I'm going to square. That's 25 times 10 to the negative 4. That's 2.50 times 10 to the 1 times 10 to the negative 4 is 2.50 times 10 to the negative 3. And that's exactly the answer. But that's how you do it without a calculator. And I know the fraction piece is tricky for you because you're not used to doing it. But with practice, you'll get there. Let's put it together. One last piece. When you want to find KEQ or Kc for a net reaction, remember in Hess's law, if the reactions sum to the net, you could do something here to find the missing piece. Very similar with one change. You're going to add the equations for individual reactions to obtain a net, but to get the Kc, you multiply their Kcs. For example, you want to get to dinitrogen monoxide plus 3/2 moles of oxygen to 2 moles of nitrogen dioxide. I look at my first reactant, I see it here. Is it on the correct side of the equation? Yes. Is the coefficient correct? Yes. Oxygen's all over the place, I don't want to play with it yet. You can see 2 moles of nitrogen dioxide right here. Is it on the product side? Yes, its coefficient matches? Yes, it does. The 2 moles of nitrogen monoxide cancel. 1/2 plus 1 is 3/2. So the sum of reactions 1 and 2 are equal to reaction 3. So what do I do with the Kcs? Multiply them. 10 to the negative 13 times 10 to the 13 is 10 to the 0. What's 10 to the 0? 1. So you're just really multiplying like 2 times 4, give or take, right there. So what I want you to try and do is this problem here. I'll reveal the answer, and hopefully you will have a head start on equilibrium constant expressions. If you take the time to write several out and solve them, which is all at the end of your chapter in your textbook, problems recommended are in your course outline, you will be very successful as we move forward in this chapter next time. So give this problem a try. I will reveal the answer. I'm going to close your eyes. I'm going to flip it to the screen so that people who are out have got it. And then we'll give you time to do it and we'll check. And like I said, practice, practice, practice. Write KEQ expressions, solve them for Kc, solve them for concentration. And you'll be very successful with these concepts in your chemical equilibrium chapter.